So we're looking at an example from section 5H of the Cambridge Year 11 Advanced text. Sine of 2x equals a half. The Cambridge text has some really helpful tips that you should use when you're trying to resolve these kinds of equations. The first thing is to always pay attention to which domain the angle can be in. So we know that sine of 2x is positive, so wherever this angle is, we know that it can only be in the first or second quadrants. But the story doesn't quite end there, because the domain says 0 to x is 360 degrees. Well, what that means is that the domain for 2x will be 0 to 2 times 360 degrees, which will be 720 degrees, and we'll see a bit more about that in just a moment. The suggestion then is to draw a quadrant diagram, and we've already established that for this example, 2x will be in the first or second quadrant, but it'll also be in the fifth or sixth quadrant because the domain is not 0 to 360, it's going to be 0 to 720. Then what they suggest you do is you draw a ray in each of those quadrants, and this is the really important part, we mark the acute angle. Now where it gets interesting is where you have compound angles, which is what we have here. We don't have sine of x, we've got sine of 2x. The author suggests you make a substitution and say, look, let u be the compound angle, and then you find the restrictions on u based on the restrictions for x, and we just talked about this. And then we solve for the acute angle. The angle that has a sine of a half is 30 degrees. From the principle of general angles, we know that u can either be 30 degrees or it can be 180 minus 30 degrees. We also know that it can be 360 degrees plus 30 degrees. And it can also be 360 degrees plus 180 degrees minus 30 degrees. Well, this gives u as 30 degrees, 150 degrees, 390 degrees, and 510 degrees. And finally, we go back and we say, well, hang on, we're not really interested in u, we're only interested in x. Well, u is two lots of x, so x is a half of u, and that gives x is 15 degrees, 75 degrees, 195 degrees, or 255 degrees. Tan of 2x equals root 3. Again, we do our substitution. Now we have tan of u equals root 3. And because tan of u is positive, u must be in either the first or the third quadrant. We've got to then look at the restriction on the domain. And we're told that 0 is less than or equal to x, which is less than or equal to 360. But because u is two lots of x, u can be between 0 and 720 degrees. We can see then that the result could be in the first or the third or the fifth or the seventh quadrant. First quadrant means we've got 60 degrees. Third quadrant means we've got 180 plus 60 degrees, because tan of theta is the same thing as tan of 180 degrees plus theta. We've got 420, and we've got 360 degrees plus 180 degrees plus 60 degrees, which is 600 degrees. And because x is a half of u, we're left with x is 30 degrees, 120 degrees, 210 degrees, or 300 degrees. Cotan of theta equals 0. The textbook suggests that you first of all change cotan into 1 over tan of theta. So 1 over tan of theta equals 0 degrees. Well, what that means is that tan of theta is undefined. Tan of theta is undefined for 90 degrees and 270 degrees and so on, which is to say when we're pointing up, pointing straight down on the quadrant circle. However, if we go and look at the cotan curve, you can see that cotan of x is 0, also at 90 degrees and 270 degrees. So you could solve it in both ways. I like the cotan solution because it's a visual way of solving it, but I really also like the Cambridge solution because it makes a lot of sense. It's got some mathematical rigor behind it. Either way, you end up with an answer for theta is either going to be 90 degrees, 270 degrees, 450 degrees, or 630 degrees. Cosecant of theta plus 2 equals 0. So the Cambridge textbook would suggest that you get rid of your cosecant ratio as quickly as possible and you convert it back to the real world. So you say 1 over sine of theta equals -2. Then you take the reciprocal of both sides of that equation and you're left with sine of theta is -1 over 2. The related angle, of course, is 30 degrees. And so we're going to be in the third or fourth quadrants, which means we've got either 180 plus 30 or 360 minus 30. That gives us 210 or 330 degrees. But we're also dealing in the seventh and eighth quadrants. So we add 360 degrees to those two results. and we get 570 and 690 degrees. Tan of theta equals root 2 minus 1. Tan of theta is positive, so we know we're in the first and third quadrants. So you set up your diagram and you go, look, here it is. In the first quadrant, it's going to be 22.5. We also have another rotation of the circle, and so we've got the fifth and the seventh quadrants. So you add 360 degrees to the first two results, and you get 382.5 and 562.5. Tan of alpha minus 45 degrees is 1 over root 3, and the solution is going to be between 0 and 360 degrees. Again, we make the substitution. Let u equal alpha minus 45 degrees. And so we're now solving for tan of u equals 1 over root 3. 1 over root 3 is the tan of 30 degrees. And because the tan is positive, we're going to be in the first quadrant or the third quadrant. And because tan of theta is the same thing as tan of 180 plus theta, our solutions are 30 degrees and 210 degrees. Now we're just going to check this off against the prescribed domain. It says, look, alpha can be between 0 and 360 degrees, but we didn't find alpha, we found u. U is alpha minus 45 degrees. So our domain for u is negative 45 degrees, is less than or equal to u, which is less than or equal to 360 minus 45 degrees. Well, that'll be 315 degrees. And happily, of course, our two solutions for u, which are 30 degrees and 210 degrees, do lie in that domain. And so all we do is we add back the 45 degrees to u, and we say, well, alpha is going to be 30 degrees plus 45 degrees, which will be 75 degrees, and it can also be 210 plus 45, which is 255 degrees.